that flow steady. We're losing heat.
Engaging the rollers now.
We need to double the output on the fuselage brackets by sundown. Move it!
We're doing fine, just keep bringing it up. Every bit counts for the war effort.
January 1942. The night air outside Detroit is frozen and silent, but inside the mill, the heat never sleeps. Molten metal glows white-orange beneath rolling cylinders the size of freight cars. Sparks scatter across concrete floors. Men in heavy gloves work without pause, their faces lit by furnaces rather than daylight. This is not a battlefield, yet the urgency is unmistakable. Every minute lost here will be felt thousands of miles away, in the skies over Europe and the Pacific. America has entered a modern war unprepared for one brutal fact. Aircraft decide survival. Aircraft require aluminum, and the United States does not have enough of it. Bauxite shipments are uncertain. Smelters are limited. Stockpiles vanish faster than planners predicted. Military orders pile up on desks in Washington faster than raw material can arrive. Fighters, bombers, transports, each demands lightweight metal that does not yet exist in sufficient quantity. In this moment of industrial desperation, an unconventional solution takes shape. Not from new mines, not from foreign suppliers, but from scrap, civilian metal, discarded frames, melted remains of a peaceful economy, forced back into service. And behind this gamble stands one man, and an idea that will quietly reshape the war itself. By the late 1930s, aluminum had become the backbone of modern air warfare. Light, strong, corrosion-resistant, and capable of being shaped into thin aerodynamic skins, it allowed aircraft to fly faster, farther, and higher than anything built a decade earlier. Whoever controlled aluminum controlled the skies. Germany understood this early. Long before the first bombs fell on Poland in September 1939, the Nazi state had invested heavily in aluminum smelting and aircraft-grade alloys. Hermann Göring's four-year plan placed strategic metals at the center of rearmament. Hydroelectric plants in the Alps powered smelters that fed Messerschmitt and Junkers factories. Japan followed a similar path, expanding aluminum capacity in Manchuria and Korea to support its growing naval aviation arm. By 1940, Axis air forces were already operating within mature industrial ecosystems designed for total war. The United States stood apart, geographically distant from the fighting, politically cautious, and economically shaped by the Great Depression. America had not yet converted its industry for large-scale conflict. Its aluminum production existed, but it was narrow and fragile. The Aluminum Company of America, Alcoa, controlled the majority of domestic output, and that output had been sized for peacetime demand. Cookware, wiring, commercial transport, and small military contracts. In 1939, American aluminum production hovered at levels sufficient for limited defense expansion, not global war. Aircraft orders from Britain and France strained the system even before the United States formally entered the conflict. Each new contract exposed a simple truth. Aluminum was not just another material. It was a strategic bottleneck. Bauxite, the raw ore from which aluminum is refined, was not abundant within the continental United States. Much of it came from the Caribbean, South America, and overseas territories. Refining it required enormous amounts of electricity. Smelters had to be built near reliable power sources, usually hydroelectric dams, and those facilities took years, not months, to construct. Meanwhile, aircraft design itself was changing. New fighters like the P-38 Lightning and bombers like the B-17 Flying Fortress required far more aluminum than earlier models. Thicker skins, internal frames, reinforced wings, pressurized cabins, all consumed metal at unprecedented rates. Every engineering improvement came with a material cost. As war intensified overseas, American planners began to see the problem clearly. Even before Pearl Harbor, War Department studies warned that aluminum production would fall short of projected aircraft needs. In meetings and memoranda, the same phrase appeared again and again: critical shortage. Yet the United States still hesitated to fully mobilize. Neutrality laws limited direct involvement. Industry moved cautiously, reluctant to invest billions without guaranteed government contracts. Expansion plans were drafted, revised, delayed, and debated. Then December 7th, 1941 arrived. Within hours of the attack on Pearl Harbor, the aluminum problem shifted from theoretical to existential. Aircraft losses had to be replaced immediately. New squadrons had to be built from nothing. Production targets multiplied overnight, but the metal required to meet them did not magically appear. America had declared war, and its air war depended on a resource it did not yet possess in sufficient volume, setting the stage for emergency decisions that would bypass tradition, monopoly, and caution alike. The morning after Pearl Harbor, Washington moved with a speed that had been absent for years. Emergency committees formed within hours. Aircraft production numbers that once seemed ambitious were rewritten in ink so fresh it barely dried. The United States Army Air Forces demanded tens of thousands of planes, fighters, bombers, trainers, transports, each one requiring tons of aluminum before it could ever leave the ground. The gap between ambition and reality was immediate and alarming. Existing aluminum smelters were already running near capacity. Power grids were strained. New facilities, even if approved instantly, would take years to come online. The war, however, would not wait. In January 1942, the War Production Board took control of strategic materials. Aluminum was placed at the highest priority level, above civilian consumption, above commercial transport, above almost everything except ammunition. Civilian aluminum goods disappeared from shelves. Kitchenware, window frames, signs, railings, even playground equipment were quietly marked as potential raw material. But allocation alone could not solve a structural shortage. The numbers simply did not add up. Aircraft manufacturers needed more aluminum than the nation could refine from fresh or in the near term. Imports were vulnerable to submarine attack. Shipping lanes were contested. Every ton lost at sea was a ton that could never become a wing or fuselage. This was the moment when unconventional solutions began to surface. Henry J. Kaiser was not an aircraft man. He had never built a plane, never run a smelter, never been part of the pre-war defense establishment. His reputation came from something else entirely: speed. In the 1930s, Kaiser had built roads, dams, and massive infrastructure projects at a pace that unsettled traditional contractors. He believed large systems could be simplified, standardized, and accelerated if bureaucracy was stripped away. During the early months of the war, Kaiser was already experimenting with mass production and shipbuilding. His yards would soon produce Liberty ships in weeks rather than months. What caught the attention of federal planners was not just output, but method. Kaiser built big, fast, and without deference to established industrial hierarchies. As aluminum shortages worsened, government officials began looking beyond Alcoa and traditional suppliers. Antitrust concerns that had once stalled diversification were set aside. The question was no longer who should control aluminum. but who could deliver it quickly enough to matter. Kaiser proposed something radical in its simplicity. America was surrounded by aluminum. It just was not in mines. It was in cities, homes, factories, and junkyards. Scrapped automobiles, broken machinery, obsolete civilian products. If new aluminum could not be refined fast enough, existing aluminum would be reclaimed, remelted, and rolled again. This was not recycling as a moral gesture. It was industrial triage. Scrap aluminum had to be sorted, cleaned, and alloyed to meet aircraft standards. Rolling mills would have to work around the clock. Quality controls would need adjustment, not elimination, to balance safety with urgency. The system would be imperfect, but it would be fast. By early 1942, scrap drives were authorized nationwide. Civilians were told their discarded metal was no longer waste, but potential wings and bomb bays. At the same time, Kaiser-backed facilities began scaling up rolling capacity, feeding aircraft plants with metal that had already lived one civilian life. Across the United States, the war entered homes not through telegrams, but through scrap piles. Newspapers printed instructions. Radio broadcasts repeated the message. Aluminum was no longer ordinary metal. It was flight time, altitude, survival. Housewives donated cookware. Mechanics turned in bent panels and worn parts. Children dragged wagons filled with metal to neighborhood collection points. The connection was made deliberately simple. This will become an airplane. Inside the mills, the pace was relentless. Shifts blurred together. Many workers had never handled aircraft-grade material before the war, yet now they were entrusted with metal that would face flak, cold, and stress at altitude. Fatigue was constant. Errors carried consequences that could not be abstracted. Still, production climbed, driven by a shared awareness that this labor shortened the distance between factory floors and distant battlefields. Turning scrap into aircraft aluminum was not straightforward. Scrap arrived in inconsistent shapes, alloys, and purity. It had to be separated, melted, refined, and rolled to precise tolerances. Engineers adapted processes originally designed for fresh ingot, adjusting temperatures, rolling pressures, and inspection standards. Perfection was not the goal. Reliability was. What mattered was consistency at scale. Rolling mills learned to produce usable sheet faster than anyone thought possible. Aircraft designers, in turn, adjusted tolerances where feasible, allowing slightly wider margins without compromising safety. Technology bent, but did not break. Time became the decisive variable. A flawless plane delivered too late was useless. A reliable plane delivered on schedule could change air superiority. Scrap aluminum shortened production cycles by bypassing or extraction and long-distance shipping. Each shortcut reclaimed weeks, sometimes months. In a war defined by momentum, those savings mattered more than theoretical efficiency. Together, human effort, adaptive technology, and tactical urgency fused into a single industrial rhythm, one that would soon test leadership, enemy pressure, and moral limits under far greater strain. Henry Kaiser's approach unsettled established industry. He bypassed committees, compressed decision chains, and accepted controlled risk where others demanded certainty. Traditional manufacturers warned of quality failures and long-term consequences. Kaiser countered with numbers. Planes were rolling out. Metal was flowing. Delays were shrinking. In wartime Washington, results carried more weight than reputation. Federal officials adapted alongside him. Oversight shifted from preventive control to corrective response. Inspectors focused on catching problems early rather than slowing output at the outset. It was a leadership style built on trust, backed by measurement, not tradition. For an emergency economy, it proved effective. Across the Atlantic and Pacific, Axis planners watched American production figures with growing unease. Germany's early air superiority rested on rapid rearmament, but its aluminum base was finite and increasingly strained by Allied bombing. Japan's access to bauxite depended on vulnerable sea routes. The longer the war dragged on, the more material constraints tightened. American scrap-based production undermined Axis assumptions. Intelligence reports began noting aircraft replacement rates that exceeded expectations. Losses that should have crippled squadrons were absorbed. Attrition calculations no longer worked. Scrap aluminum symbolized total war. Civilians became suppliers. Waste became weapon. The boundary between home front and front line dissolved quietly, without spectacle. This mobilization was voluntary in appearance, but existential in reality. Participation was framed as duty, not choice. By mid-1942, the system faced its ultimate test. Demand surged again. Losses mounted. Production targets doubled. The question was no longer whether scrap aluminum could supplement aircraft manufacturing, but whether it could sustain the pace required to turn the war itself. That answer would be forced into clarity during the most intense industrial stretch of the conflict. By mid-1942, the aluminum crisis reached its breaking point. Aircraft losses were no longer theoretical projections. They were arriving as daily reports. Planes shot down over the Solomon Islands, bombers failing to return from Europe, trainers crashing under accelerated schedules. Every loss triggered an immediate replacement order, and every replacement demanded aluminum that did not yet exist in comfortable surplus. The numbers escalated faster than infrastructure. In 1941, the United States produced fewer than 20,000 military aircraft. In 1942, the target exceeded 45,000. By 1943, it would surpass 85,000. Each increase compressed timelines and narrowed margins. There was no longer room for gradual scaling. The system had to leap forward or fracture. Inside Kaiser-backed rolling mills, the leap was already underway. Facilities ran 24 hours a day. Maintenance windows vanished. Machinery was serviced while still warm. Scrap aluminum arrived by rail and truck in unending streams. Unlabeled, mismatched, and imperfect. Sorting yards worked under floodlights. Metallurgists tracked alloy composition batch by batch, blending scrap with newly refined metal where necessary to stabilize strength. The mills did not stop. Sheets rolled thinner. Output accelerated. Inspection protocols adapted in real time. When defects appeared, adjustments were immediate, not debated. The objective was not elegance, but survival through output. At aircraft plants, production lines felt the change almost instantly. Aluminum deliveries became more regular. Stockpiles appeared where emptiness had dominated weeks earlier. Wing assemblies moved without delay. Fuselage frames advanced down lines instead of stalling at missing components. The war economy, previously choking on scarcity, began to breathe. This shift did not go unnoticed in Washington. By late 1942, War Production Board data showed a decisive inflection. Aluminum availability, once the primary constraint, was no longer the dominant bottleneck. Labor, engines, and training pipelines now competed for attention. The material crisis that had threatened to cap air power expansion had been broken. The transformation was not clean. Scrap-based aluminum sometimes required additional reinforcement. Engineers compensated with design tweaks. Aircraft manuals reflected incremental changes. Pilots never knew which parts of their aircraft had once been civilian goods. The metal was anonymous by the time it reached altitude. What mattered was that it held. In Europe, the effect became visible in the sky. Bomber formations grew larger. Losses remained heavy, but replacement rates erased their strategic impact. The 8th Air Force could absorb damage and return stronger. In the Pacific, carrier air groups replenished faster than Japanese planners anticipated. Attrition, a calculation once expected to favor the Axis, began to tilt decisively. By early 1943, aluminum production in the United States had more than doubled compared to pre-war levels. Scrap was no longer an emergency substitute. It had become a normalized input. New smelters were coming online, powered by massive hydroelectric projects, but the critical gap had already been bridged. This was the turning point. Not a single battle, not a single order, but a moment when industrial momentum crossed a threshold from fragile to unstoppable. From this point forward, American air power would no longer be limited by metal. The Axis never fully recovered from that realization. German factories struggled under bombing and resource depletion. Japanese production faltered as shipping lanes collapsed. Meanwhile, American mills continued to glow through the night, feeding aircraft lines that no longer paused for want of aluminum. Scrap had become structure. Improvisation had become doctrine. And the war's balance, once uncertain, now shifted with mechanical inevitability toward an outcome forged far from the front lines. Inside furnaces, rolling mills, and factories that refused to stop. That momentum carried forward, reshaping not just the war's middle years, but everything that followed once the guns finally fell silent. By the end of 1943, the consequences of America's aluminum breakthrough were no longer measured in shortages avoided, but in scale achieved. Aircraft production reached levels that would have seemed impossible just 2 years earlier. In 1944 alone, the United States produced nearly 96,000 military aircraft. Fighters rolled out by the hour. Bombers emerged in steady succession, their aluminum skins indistinguishable from those built with newly mined metal. The bottleneck that once threatened air power expansion had vanished entirely. This abundance reshaped strategy. In Europe, Allied planners no longer rationed aircraft to conserve material. Losses over Germany were anticipated, planned for, and absorbed. Strategic bombing campaigns expanded in size and frequency. When aircraft failed to return, replacements were already en route to the front. Attrition, once a risk, became a calculated tool. German industry, constrained by limited aluminum reserves and battered infrastructure, could not match the tempo. In the Pacific, air superiority followed a similar arc. Carrier groups rotated aircraft rapidly. Training pipelines widened. Experimental designs moved from drawing boards to flight lines faster than Axis intelligence could track. Japan's dependence on imported bauxite became a fatal vulnerability as shipping routes collapsed under submarine pressure. Aluminum scarcity forced compromises in aircraft design and maintenance, further widening the gap. At home, the scrap-driven system left a permanent imprint on American industry. Recycling, once marginal, became institutionalized. Sorting, alloying, and reprocessing methods developed under wartime pressure evolved into standard practice. Post-war factories inherited techniques born from emergency, turning improvisation into efficiency. Henry Kaiser's influence extended beyond aluminum. His approach, prioritizing throughput, decentralizing decisions, and accepting calculated risk, became a model for Cold War production. From jet aircraft to missiles, American industry embraced scale as strategy. The lesson was clear. Industrial adaptability could outweigh raw resource advantage. The human cost remained visible. Mills wore down workers as surely as they wore machinery. Accidents, fatigue, and strain were part of the price paid far from the battlefield. Yet the psychological shift endured. Civilians had seen how quickly ordinary life could be transformed into war output. That knowledge did not fade when peace returned. By 1945, aluminum was no longer scarce. New smelters, expanded dams, and matured supply chains ensured abundance. But scrap metal's wartime role remained quietly acknowledged in reports and archives, a reminder that victory had depended not only on innovation, but on reclaiming what already existed. The war ended with surrender ceremonies and headlines, but its industrial aftermath continued shaping decades of production, planning, and preparedness. And beneath it all lay a simple truth forged during crisis. Modern wars are not won solely by those who possess resources, but by those who can reshape their use when necessity demands it. The story of America's aluminum in 1941 to 1943 is a quiet victory, often overshadowed by headlines of battles and bombs. Yet it reveals something profound about modern warfare. The battlefield is not limited to trenches, skies, or seas. It extends into factories, rolling mills, and even suburban neighborhoods where discarded metal became wings, fuselages, and life-saving machines. The crisis demonstrated that resources alone do not guarantee power. Raw bauxite, smelters, or hydroelectric dams were insufficient without human ingenuity, leadership, and urgency. Kaiser's improvisation turned scarcity into strength, showing that industrial flexibility could match, and sometimes exceed, strategic necessity. It also redefined the relationship between civilian and soldier. Citizens contributed through kitchens, garages, and workshops, understanding that their scrap was not waste but part of the war's pulse. Aluminum became a symbol of collective effort, the quiet, uncelebrated labor that ultimately dictated air supremacy. By war's end, the United States had not only overcome a critical shortage, but had reshaped its industrial identity. The techniques, disciplines, and mindset born from emergency became a template for post-war production, Cold War readiness, and even modern logistical planning. In the glow of those furnaces, in the hum of rolling mills, history was quietly forged. What began as an absence of metal became a demonstration of resourcefulness, endurance, and strategic imagination. The aluminum that once did not exist in sufficient quantity ultimately became the backbone of victory, proof that in total war, ingenuity often matters as much as raw material, and that even the smallest scrap can carry the weight of history.